We have a theory which is called quantum electrodynamics. The physics has got a history, at least a theoretical history, of synthesis perpetually. Of course, the experiment is always finding new phenomena. The problem is to work them together, and sometimes we see that they're different aspects of the same phenomenon. An example is, of course, the simplest and earliest one is that the laws of motion explain the properties of heat, because heat was motion, and if you knew how motion worked, you could understand the thermal properties. It also explained the properties of sound, which is otherwise a mystery, as the motion of the atoms and waves in the gas. Newton, who gave us the laws, worked out the laws of motion, also gave us another theory about the forces between large masses and distances from one another, called the theory of gravity. As the time went on, phenomena associated with electricity, rubbing combs in your hair and things like that, and magnetism became interesting to the experimental physicists, and they discovered the relations between them experimentally until they saw, ultimately, that it was not two different phenomena, but different aspects of the same thing. Another phenomenon that Newton had studied was light. So without time, it looked at first like there were many things: motion and gravity, electricity and magnetism later, and light. But when Maxwell put together the laws of electricity and magnetism, he found out that the behavior, that the equations that he had produced expectation that would be behavior of waves that would propagate at a speed which was figured out from electrical measurements, but came out the same as the speed that light actually propagated. And so there was a new theory of light, which is that it was an electromagnetic wave, and Maxwell's great synthesis in 1873 was to connect electricity, magnetism, and light. Light is just one aspect of the electromagnetic wave, which can have different kinds of wavelengths from that point of view. And if you have different wavelengths, if the wavelength is very short, between about 400 millionths of a centimeter and 700 millionths of a centimeter, then you see it directly with the eye. But if it gets longer, the wave is, well, it's a long end, it's red, and on the other end it's blue. And if it gets more longer than the red, we call it infrared. The rays are there, but the eye doesn't see them. The pit viper has an eye that sees the infrared. And if you go in the other direction to beyond the violet, then we can't see it again, but the bee has an eye that sees the ultraviolet. And if we go still further to the far ultraviolet, no animal has it that can see it, but we can make instruments that detect it, or photographic plates, and so on, up into X-rays and so forth. And down in the other direction, far infrared, you get into radio waves, and we can build instruments that detect them, and we can use them to advertise soap. In addition, so that is an enormous range of one property, the wavelength. A range of phenomena that's a complete, enormous spectrum. The spectrum we see with the eye is a very narrow range, and it's the entire spectrum. It's all put together with the one theory of electromagnetic waves. I'm going to talk about that part of it, and I'm going to call it light, instead of saying electromagnetic radiation. Light is what we see, is only one little part, but from the physicist's point of view, the accident that the human eye happens to be sensitive to waves from here to here is not essential. The phenomena are the same over the whole range, and I'm going to call them all light, but it could be radio waves or X-rays or what have you.